And lastly, hopefully this is not an issue one little bit, but if we have any unintended guests who join us today and cause any havoc, I'll go ahead and end the meeting immediately and hopefully get us out a new invite as soon as that happens. But I feel like because we cover this, it won't happen. So with that being said, I'm going to go ahead and hand this over to Beth Schuler, who's going to let us know about our speaker today. And we're looking forward to having a discussion as a community. Thanks so much.
Thanks, Shannon. Hello, everybody, and welcome to our Ed Policy seminar today. I think I know nearly everyone on the call, but if not, I'm Beth Schuler. I'm on the faculty here as part of our Ed Policy group. This talk is part of the Ed Policy Work seminar series that's been generously sponsored by the Bankard Fund for Political Economy. Please mark your calendars for our next speaker, who will be Rashid Malik. He's the director of early childhood policy at the Center for American Progress. So that should be a good one. And there's details on our website. But today I am delighted to welcome my colleague, Jim Soland, who is an assistant professor of quantitative methods here at the University of Virginia, and is also an affiliated research fellow at the assessment nonprofit NWEA. Jim is doing some of today's most exciting work in educational and psychological measurement, which I'm certain he would self-deprecatingly say is a low bar for excitement, but I would absolutely describe it in those terms as exciting and important, even beyond the world of psychometrics. Part of that's because, you know, he studies things that are kind of happening under the hood that many of us applied researchers take for granted, and sort of helps us see what we've been doing in really new ways, but also just because of the timeliness of the topics that he studies. So just as an example, he's kind of recently documented national trends in kind of achievement across COVID impacted school years in a study that I've had multiple occasions to cite already. So he's doing great work. He's also a person who's just really generous with his time and expertise. So we're lucky to have Jim as part of Ed Policy Works, lucky to have him here today for the speaker series. And with that, I will hand it over to Jim. Take it away.
Well, thanks so much for the kind introduction, Beth, and great to see all of you. Yeah, I'd go a step further. I think that saying that psychometrics and exciting is actually an oxymoron. I'm not sure that exists out there in reality. My advisor always used to say, people who study psychometrics, like deep down, really truly wanted to be accountants, but just couldn't stand the excitement. So I think that kind of sums up the mindset a little bit. But let me share my screen here, see if we can get the slides up. Can people see this okay? Great. So I'm going to be talking a little bit today about some of my work around how scoring surveys can affect your study's results. I call it a trip through the IRT looking glass, because even for those of us who do item response theory a lot, there are so many decisions that go into this, and it can be a little confusing at times, even having done this work a whole bunch. So part of this work, which I did jointly with Megan Kuhfeld at NWEA, was for us to wrap our minds around all of the decision points related to this. So as I always like to say, I study latent variables. And the reason I talk about it in those terms is because it kind of cuts across psychometrics, item response theory, structural equation modeling. And I think it's helpful for students to know that there's this sort of big unifying theory underlying a lot of these different methods that we talk about, even though you get them as discrete courses. I think everybody here knows me a little bit and knows my background, but just in case people wonder why I shuffle down the sidewalk in my bathrobe talking about latent variables, my background and how I came to all of this is actually from a policy perspective. I started off working for the state legislature in Massachusetts at a time they were really debating school turnaround and how you identify low performing schools. And I was always struck by just how much some of the details really seem to be at the heart of some of these decisions. And after that, I ended up being in California working for the Legislative Analyst's Office at a time when Arnold Schwarzenegger was the governor. And when the core districts were just starting to use a lot of their social emotional learning outcomes. And so I was always just really struck again by how often these seemingly arcane, like technical decisions seem to be at the heart of really fundamental questions around equity and fairness in education. And then that was confirmed for me when I went to NWEA and a nonprofit in Portland. And for those of you who are wondering, yes, that is a gentleman dressed as Darth Vader, wearing a kilt, playing a bagpipe that creates flames on a unicycle. He is a real guy. He's out and about in Portland. So just a little bit about my background, and that a lot of this technical work I do comes from a desire to really focus on these important questions of equity and fairness and education and accountability. So I'm going to talk about today, just so you have it from the outset. Here's a citation to the working paper that we've been doing. One of the reasons I point this out is that you can find the full paper, including some of the model formulas, path diagrams, and code for all of these different things here in this folder. And really, I think that the coding piece is especially important if you want to know how to fit these models. You can have these as a resource, and I'm happy to help you. And it's really in line with this idea that I really think of a lot of my work as being translational and being an opportunity to help people do better quantitative social science and avoid common traps that they can fall into. I should mention, so this is the original version, but since we first started, Kelly Edwards has come on and been a really valuable co-author on all of this. So I would be remiss if I didn't mention her as well. Just a quick outline. And again, I know this has already been said by Shannon, but please do jump in if you have any questions as we go. I'd like for this to be as interactive as people would like it to be. But I'm going to talk a little bit about the motivation for this particular work. And the way it's structured is we essentially walk through 4 really common study designs and then show how those study designs are impacted by the ways that you score your measures. And so those correspond to the scoring decision stages that I'll enumerate, and then get to the most important part, which is how do these scoring decisions affect results, and then get to some concluding thoughts. So first, by way of motivation, I feel like a lot of you have heard me talk about this stuff before. You've heard me motivated in various ways. And so rather than stick to one, I'm actually going to mention a few different possible motivations for all of this work, all of which clearly come back in my mind to measurement on some level. The first one is there are a number of long-standing debates in education with real implications for equity. So as an example, there's big debate about whether achievement gaps on the basis of socioeconomic status have widened or narrowed over time. People are debating whether summer loss is even a real phenomenon or if it's just a test artifact. Do schools make inequities better or worse? Are growth mindset interventions effective? Like, all of these things are still fairly hotly debated, and no one can quite put their finger on what's happening, why there is so much debate. And as Tom Kane said, what's at stake is basically understanding the last 30 years of education reform. So clearly some stakes attached to understanding these things. The second motivation is just, there's been a lot of talk about the replication crisis, that studies in psychology don't replicate. And there's been some talk that measurement might be at the heart of this. And I know education doesn't quite have the same type of replication as in psychology. You can't just do the same study over and over again in a lab and see what happens. But certainly you can have cases where you implement something in a couple of different contexts and the results may or may not remain the same, or even lots of different contexts, and there's not always consistency. A third one is around clinical work, and this is a little more in the psych realm, but certainly applies to education, is that there's so many clinical decisions getting made on the basis of some of these measures, including short survey measures, and people oftentimes don't realize just how much measurement decisions can affect these. And so as a key example that I've used before is if you look at something like the Beck Depression Inventory, it's a high stakes assessment because it's often used as an outcome in clinical depression trials and to diagnose patients. The primary BDI validation study has been cited over 12,000 times. This was even a couple of years ago. But in practice, the BDI is scored differently than the original validation study, and the model used in most of the studies that employ it fit extremely poorly. So a lot of these clinical studies and decisions are getting made based on a measurement model that is not really justifiable. And the fourth is just that social emotional learning is becoming very mainstream and very widespread at this point. And so, as I mentioned, there are still debates nonetheless about whether growth mindset interventions really work and how important is self-control to educational achievement and attainment. Is belonging a key to success in college? And on the self-control piece, people have been revisiting the marshmallow study a lot in recent years, and there's been huge debate about this and the importance of self-control. So all of these things are fundamental to the importance of social emotional learning, SEL. And in the core districts where I do a lot of my work and with whom I do a lot of my work, there are over 1.5 million kids who are getting these SEL surveys every single year. And yet there are these basic things we don't know about SEL itself and about the measures that we use to actually quantify things like growth mindset or self-efficacy. So I'm certainly not the first to bring all of these different issues back to the idea of measurement potentially being a culprit and replication failures or longstanding debates in education. For example, there's a great educational researcher piece by Duckworth and Yeager where they described advantages and disadvantages of these different types of measures. And then Wolf in 2021 reviewed hundreds of studies from the Works Clearinghouse and found that the particular measure used as the dependent variable was by far the strongest predictor of differential findings across studies. Oftentimes with, a lot of the studies are based on researcher developed measures, I think is sort of the euphemism that she used, but really has huge implications. But then in most cases, these studies are really focused on what type of measure you use, what type of survey you use, and much less on how you score them. And I think that's partially because most educational researchers are intimately familiar with this idea of random or classical measurement error. You measure things imperfectly, there's noise in your measure. It might, make your standard errors a little bit bigger. It might attenuate your regression coefficients a little bit, but by and large, it's not going to wreak havoc on your results. But I think there's less familiarity with the bias that measurement models and the ways that we score things can introduce into the estimates we care about. And this is bias both in terms of, are we situating people right on this latent continuum, this place where we want to see where someone lands in terms of their self-efficacy and growth mindset. But in turn, when that's biased, the treatment effect estimates we have, the growth estimates we have, all of those downstream uses of scores can also be biased in turn, as I'll show today. And it's especially pertinent when we're talking about extremely short socio-emotional learning surveys. A lot of what I talk about is still applicable to achievement tests, but part of the reason the survey piece is the key is like the core district surveys are often 4 or 5 items long. So they're very, very brief. And when you only have a few items in your measure, the stakes get a lot higher in terms of the type of bias that can get introduced. So I'll move on now to the study designs. And again, I'll pause after this section and see if people have questions. But if you have any questions, thoughts as I go, please do let me know. But these study designs are essentially, we're going to look at 4 common study designs, common ways that people use social emotional learning scores in their studies. And those will be the basis for looking at how scoring decisions affect things. So a couple of quick caveats, and I already alluded to this a little bit, but I'm going to focus on surveys here just because that's been sort of the focus of mine related to social emotional learning. But I should really point out that these apply equally, if not even more so, to things like observational protocols, observing teachers teaching, and I'll touch on that actually at the end of the talk, and does still apply to achievement tests to a certain extent, although less so, again, if the test is longer and more reliable. But so again, I'm going to focus on surveys, but keep in the back of your mind that I could equally write this paper for some of these other measures that we frequently use. The other thing to mention is I'm going to focus on the group and not the individual. So oftentimes when people think about item response theory, they think, well, there's just basically like one way to get at it, one type of model you fit, you produce a score, and that's the decision is, should I use IRT or not? But one of the tricks is that things change quite considerably if you want to make inferences about a group. So achievement gaps or control treatment contrasts or differential growth over time. And so a lot of these decisions I'm going to talk about today related to scoring would just be off the table if all we are trying to do is figure out if a very specific student was eligible for an intervention or something, or if they were going to like proceed on to high school in the case of an exit exam or something like that. So these are really for group inferences. And these practices are really common that I'm going to talk about in the context of achievement tests. This is one of the reasons you have to worry about it a little less, is because tests like the PISA, where all they really care about are comparing countries, not individual students, already does a lot of this. It's just that it's almost entirely absent from any research that uses surveys or teacher observational protocols or the like. So the first design is, and these are going to be broken down by single group, single time point. So the first study design is very simple. We have a single group at a single time point, and we want to understand the variance in the scores. I actually just, was looking for a visual, and I found this normal curve, and I don't know where the superior, very superior gradations came in, but I'm pretty sure these labels are not the way you should use the normal curve. But in any event, works as a visual. So in the first case, all we are trying to figure out is maybe we have growth mindset scores for a group or even a couple groups, and we want to just know how variable they are. The second study design is we now have two groups, but a single time point. And so kind of a key example here might be, well, we have a control treatment comparison, and we just have their post-test scores. Or we want to know if there are male-female differences in something like self-efficacy. So again, two groups, but a single time point. The next study is then we have one group and multiple time points. And sort of the classic example of this would be we want to look at growth in some of these constructs over time. So, here we have linear slope estimates for self-efficacy and growth mindset and self-management. And so this is the case where we might have one group at multiple time points. And as you'll see in a second, all of this is relevant because you can tailor your scoring models dependent on the group, number of groups and number of time points you have in your model. So here's a case with multiple time points. And so the classic example of this type of study would be looking at something like growth. And then finally, design 4 is two groups and two time points. And so again, here we could return to the randomized control trial example, but we would have a pre and a post group control and treatment. So you can think of that as two groups, two time points, pre-post control treatment. And that's a case where you could factor that study design into your IRT model if you so chose. And the other example that pops up that I'm not going to focus on, but in multiple groups, multiple time points, this also becomes really relevant if what you want to do is understand how differential patterns of achievement occur over time, because there you have, maybe public versus rural schools, you have multiple time points. And so you have multiple groups and lots of different time points. And so I'm going to focus on these very sort of clean, straightforward examples of a couple groups, couple time points, but you could even employ what I'm doing in the case where you have lots of time points and several groups that you want to look at. So that's the general setup. Those are the study pieces, but let me pause for a second and just see if anybody has questions at this stage about the setup. I think it's pretty straightforward. But now we'll get into the scoring piece, and things will get a little dicier. So I think oftentimes when I talk to people who don't do measurement work, they tend to think, well, there are a couple of options. Like I could either use item response theory or not. I could just total up my scores, my item responses, and get a total score, or use a measurement model. But the key is that's just one of sort of 4 big picture decision stages. So that first one I mentioned is just, should I use a measurement model or not? Should I use IRT or structural equation modeling or something like that to produce a score? But then from there, there's a really important question of like, okay, you've decided to do that. Which measurement model should we use? It's not so simple as just saying IRT or not. And from there, so you have a measurement model and you should say, how should I estimate the model's parameters? And one way to think about this is, it's really just like if you have a regression model. Let's say you already have your scores, you're doing regression discontinuity or something. You have to think about what model you're going to fit, how you're going to estimate it. And there's a direct parallel here, which is you have a measurement model to produce a score. You have to figure out how you're going to estimate those parameters. And just like you can have bias in your regression discontinuity model, you can have bias in this type of measurement model. And then the last piece that also really, I think, gets obscured is that there are a whole bunch of different ways that you can produce scores. So once you've settled on whether to use a model and what that model is and how you're going to estimate it, you can then ask that IRT model to spit out scores in a bunch of different ways. And that piece ends up being oftentimes one of the most consequential for study designs and bias that can get introduced into studies. So this is going to be way too overwhelming to really look at in detail, but I just wanted to point out that in the paper, we have this sort of like decision chain where it's like at each stage you say, am I going to use a measurement model? Yes or no? How many groups do I have? 1 or 2. And so if you're trying to figure out how to navigate this maze, you can sort of follow these paths, and it's a little like a choose your own adventure. So you can do this flow chart and sort of see what your options are. And then in the paper, we point out like, well, if you get to this point, here's the code that you might use if you get down to here, or here's the code you might use if you decide on this. And the whole point of the talk today is that you can know like what the implications are of the different choices you're making and have the right tools to address them. So now I'll walk through each individual stage and hopefully demystify a little bit what's entailed and how to think about them. So the first one is just, should I use a measurement model or not? And what people oftentimes do, as most of you have heard me talk about, is you just score your survey by producing a total score, which is if you have 4 items and they're Likert type responses or 0, 1s, you just add up those numbers and get your total score. So if these are 0s and 1s, like yes, no questions, it would just be however many you said yes to, that's your total score. And the thing to know about this approach is that it's equivalent to essentially saying it's 1 times item 1 plus 1 times item 2 plus 1 times item 3. And so you are unit weighting all of these items. You are essentially saying, I think every one of these items should get the same weight when I'm trying to situate someone on this latent continuum, this, this scale that I can't quite see. And as McNeish and Wolf pointed out, this approach technically involves no measurement model. You're not estimating anything, but it's equivalent to fitting an extremely constrained measurement model. So people think, oh, well, I'm just adding things up. I'm not making any assumptions, but actually this implicitly has huge assumptions that are very restrictive and very rarely met, especially in the case where you have multiple time points or multiple groups. All of the assumptions, this weighting assumption gets way more problematic and complicated as you layer on groups and time points. And kind of the classic example in this case that a lot of you have also seen me use is if we were going to have a depression survey, and this is a real depression survey, you might have one item that's asking about trouble falling asleep. You might have another that's asking about doing physical harm. Those two things at face value have very different implications and should potentially get different weights. But most studies looking at depression give these things the same weight. And so again, the way to think about that is if I select, 1 for item 3 and then 2 for item 9, or vice versa, I get the same sum score. So my score is going to be 3 in either case, and there's no distinguishing the fact that one person might have said several days and more than half the days, for one set of items, and it's the reverse set of items for the other person. So there are lots of trade-offs involved in whether or not to use a measurement model, but that weighting piece is usually the biggest one. So I think at this point, I've kind of, belabored that point probably with all of you, since you've heard me chat about these things before, oftentimes. But the next thing to decide is, okay, let's assume for a second that you're a little worried that maybe the item shouldn't be weighted right. You're going to use a measurement model. The big question there becomes what type of measurement model, and in particular, how many groups and how many time points do you have? So for example, one option might be you can, if you have treatment and control groups, if you just fit the standard IRT model that comes in your, R package or the Stata IRT software, what it's essentially going to assume is that you have one group, which means, in your population, there is one mean and one variance to those scores. Whereas if you think about it, probably these scores should have separate means and separate variances. I mean, especially for control and treatment, post-treatment. If the intervention has worked, most of the time you would have different means and different variances. And so you might want an IRT model that actually acknowledges that difference, that's how the data were generated. And the same goes for these questions of growth and even growth by group, is that if you have multiple time points, if you just fit your garden variety IRT model, what it is saying is, I think even though we're going across a whole bunch of different time points, there's really just one mean and one variance in the population. Whereas if we even just look at something like math achievement, I mean, we all sort of know that it tends to go up over time and becomes more variable as kids move through school. And that will still kind of sort of show up in the scores if you just use your regular IRT model. But as I'll show, you end up damping those things down quite a lot without acknowledging in the measurement model that there are those differences by group and by time point. And then again, for the people, if anybody wants to see sort of the path diagrams, the equations that correspond to these, the typical item response theory model has a single latent variable, and these would be like your 3 survey items. And so this is what we assume. There's one mean, there's one variance to this latent thing that we can't see, your growth mindset or self-efficacy. Whereas the models I'm talking about, you could end up having multiple groups and multiple time points. So this might be like control treatment, time 1, time 2. So you could actually have a model that acknowledges that there are actually really 2 groups and 2 time points. So you would have 4 different means and variances, as opposed to just assuming that there's one mean and variance, regardless of whether it's pre, post, or control treatment. And again, all this technical detail, I'm going, as you can tell, I'm going very light on the technical detail today, but it's all there in the appendices for anybody who want to look at them in the paper. And then in terms of this third stage of parameter estimation, like, okay, so let's say I've decided on a measurement model. I may have even been convinced that I should have a measurement model that has multiple groups or multiple time points. The one real question, we don't talk a lot about this stage 3 of how do I actually estimate the parameters in the model, mainly because there's been a ton of good work on that already, and it gets kind of even more technical than some of the stuff we're talking about today. But the one question you do have to have in the back of your mind is just, do I have enough people to do these IRT models? So unsurprisingly, what we usually really find is that virtually all the time you're going to want to be doing some sort of IRT model if you care about group comparisons or multiple time point comparisons. But if you're in a situation where you have 200 or fewer people in your study, then that's essentially in the territory where you might actually do more harm than good by reverting to IRT, because you just can't sufficiently estimate everything that's in that measurement model. So really stage 3 is just a caveat at this point. And then stage 4 is really the big one, I think, because this is where like all these other decisions that you made along the way end up becoming really consequential. So again, this is, you've decided that you want to use a measurement model. You want that model to spit out scores that you can use in your analyses. There are a bunch of different ways you can do that, but I'll just focus on a couple here, which is, should I use maximum likelihood estimation? Which, and this parallels just any type of modeling you do. It's not specific to IRT, but if you use maximum likelihood, you get the smallest standard errors, it's unbiased, so there are a lot of things to like about it. But you also have these Bayesian approaches, like expected a posteriori or EAP scoring. And that approach directly accounts for uncertainty. As I'll mention, it actually has a few, it helps mitigate some of the problems that can arise with maximum likelihood. So there is a real trade-off here. And in particular, so thinking about how scores deal with uncertainty, if you aren't sure about a particular kid's score, it's a noisy score, then maximum likelihood is really not going to do much to take care of that. It's not going to address that in any way. Whereas if you you produce your scores using EAP, which is that Bayesian approach, what we say is, well, I'm not sure about this kid's score. I'm going to just scrunch it towards the mean. I'm going to shrink it towards the mean. And we'll address uncertainty by saying you're probably a little closer to the mean than this is actually really saying. And for those of you who do value-added estimation, fit those kind of models, this is exactly the type of decision you make, which is, do I include some sort of like empirical Bayes shrinkage or do I not? Same thing going on here. Do I shrink uncertainty in the scores or do I not? And one of the reasons this is really important is, so let's imagine a case where you have a control and a treatment group. If you assume that there is just a single group in your model, in your measurement model, and you use EAP scoring, what that's going to do is shrink to just a single mean. So if you have, a control group that has a lower mean than the treatment group, what you're essentially doing is shrinking the control group towards your average and the treatment group, downwards towards that average. So you're essentially pulling your control and treatment groups towards each other, such that you are very plausibly going to just wash out any true control treatment contrast you have. And this issue comes up all the time, because like oftentimes if you're going to use like an IRT software to produce scores for something like a survey, it will default to EAP scoring. So for people who really care about these control treatment contrasts, you could very easily have a case where you are unintentionally washing out control treatment differences or whatever two groups you really care about. The other thing that can crop up here.
Hey, Jim, sorry, can I ask something real quick on this?
Yeah, please.
Is there, so the conventional wisdom, at least I understand, how I understand it about shrinkage is, if it's going to be a left-hand side variable, don't shrink it. If it's going to be a right-hand side variable, shrink it. Is that a generally correct statement about the conventional wisdom, or is there more nuance?
I mean, I tend to think of that distinction a little less firmly. I mean, because essentially what we're talking about here is cases where this is the dependent variable and you do want to potentially shrink it. And to me, the real distinction becomes, again, like what is the purpose that you're using this for? Like if you were ever going to do this in some way to try and predict something for a given student or a given school, I think there's a pretty good argument against using this kind of shrinkage. But if what you really want to do is say like, well, what are these mean group differences between control and treatment? As I'll show, you do a much better job of like detecting those true differences if you include the shrinkage. And I think the sort of individual piece ends up becoming especially important, because you could imagine a case where, like, if you were to ever use this in the context of looking at individual scores, you could have a case where a kid falls below some cut score such that they would get a growth mindset intervention on their maximum likelihood estimate. And then their EAP estimate might pull them back towards the mean such that they'd no longer be eligible for that intervention. So if there is in any way going to be like an individual use of the score, then like I think that logic 100% holds up. It's just more debatable and more nuanced in the case of multiple groups and aggregate level inferences.
Gotcha. Thanks.
Sure. So the last thing I'll mention on the scoring front, and then I'll just pause and see if there are other related questions, is one of the things you don't run into so much with achievement tests, although you certainly can if you have a really hard or easy test. But let's say for a second that you have a kid who just selects the top response category, and I say I couldn't, so having trouble finding an image where they select the top category. So just assume for a second the little red check mark is in this agree completely box. And so you have a 4-item survey, and they do that for every single item, such that you only get agree completely. If you use maximum likelihood as your scoring approach, that score is undefined because you're essentially trying to maximize or minimize some function that is just undefined out of those extremes. And so you don't actually get a score. And there are really two options in that case. One is you just treat that score as missing. The other, that again is a software default that a lot of people don't even realize when they're using IRT, is that some arbitrary maximum or minimum will get dumped into your data set. So for example, oftentimes, like they might just say, well, we don't know what your score is, but let's just say it's 3 standard deviations above or below the mean. And so that could certainly be the case. Like if you have a 4-item survey, it happens all the time that people will select the top or the bottom response category. And then if you just sort of like click the IRT button and go on your way, you will get arbitrary scores added into the mix. And there are pluses and minuses to doing that, as opposed to using something like the Bayesian approach, which does not run into this issue that I'll get into a little bit. But again, this is one of those things that happens a decent amount under the hood without people even realizing it. And I've even been in the case where I get my IRT estimates and I look at them and something seems strange, and I realize, oh, they're actually, a 10th of these scores weren't actually estimated. They were just missing and had something dumped in there. So I'm going to pivot to talking about the effect of all these different decisions on the results, but let me just pause one more time and see if people have questions. Okay.
Jim, this is Vivian.
Yeah.
I had a question. So it's interesting that you talked about sort of like potentially addressing sort of replication issues. So is the process that you outlined here, would this be useful for researchers to think about, for example, in the pre-registration, right? Like, would you recommend that folks sort of go through that chart, that decision tree chart, and basically lay out in advance what their decisions would be in advance about how they would choose to score? Or is this something that researchers are choosing as they're looking at the data? Like, what would you recommend here?
Yeah, thanks for the question. And that's one thing I think we mentioned in the paper, but I hadn't really, wasn't really going to call out in the talk specifically, is that, I mean, I think an ideal scenario would be if you're looking at something like What Works Clearinghouse or pre-registration or what have you, you should actually say exactly how you're scoring, even if it's just, like a 1 or 2 word answer to each of those 4 stages. That would go a long way towards helping sort things out, because as a preview of the findings, some scoring approaches coupled with certain measurement models really tend to increase type 2 errors, whereas others will really affect type 1 errors. So you can get really different results in terms of like proportion of significant results in these simulation studies, dependent on the different combinations you have. And right now, the What Works Clearinghouse basically mentions, I don't think it mentions scoring at all. It says if you have measures that suffer from some degree of unreliability, you have to try and address that. But it doesn't mention item response theory. It doesn't mention anything about scoring. And so in some ways, this is specific to social emotional learning, but also I'm working on a paper now where we employ some of these models with achievement tests and show that some of the problems I'm about to point out are less severe when you have longer, more reliable tests, but they certainly crop up and can really affect type 1 and type 2 errors. So long answer to your question, but the short answer is yes, I think that would be ideal if people pre-registered how they're going to score the measures.
Jim,
go ahead, Walter.
Can I ask a question? I don't know if this is the right time, but so as somebody thinking about, SEL is being treated here, I believe, and in much of education as though it's a skill that one gets better and better at, like reading. And so that you're really trying to see how SEL good people are. And you're looking for interventions to improve those skills. Versus it's more of a, like depression, it's a characteristic, so to speak, and you're trying to, the questions are designed more to ask enough times, you probably get some reliable distinction between people.
Mm-hmm.
So the items are meant to be repetitive rather than each one representing a specific necessary content or representing a greater degree. So I don't, if this is the wrong time for that question, we can move it to later, but I'm real interested in how that affects some of the stuff you're talking about here and how you think about SEL, given that you probably spend as much time on measurement as anybody with SEL.
Yeah, well, I'll give you one answer now, and then we can talk at length about it more, either at the end of the talk or some other time, Patrick. But I think for some things like self-efficacy, there's a lot of theory clearly suggesting that there are developmental trends to these, that there are patterns. And so really a lot of these scoring decisions are about the degree to which you can detect those differences and accurately estimate them. And so one of the things I'll show is that your growth estimates can shift a whole heck of a lot depending on how you pair these different choices that you have along the way. But then I think there are sort of constructs, like depression, anxiety, where it tends to be more state trait, and it's unclear which those are. And so for those, I tend to use a class of models that actually is more like decomposing how much of the variance is consistent over time versus idiosyncratic to a time point. And I actually was kind of working on a paper related to this, which is you probably get pretty different results in your randomized control trials if you actually account for sort of, is this state variance, kind of bouncing around, or is it trait variance? It's consistent over time. And what's your theory for what gets impacted? Like, should this be impacting them on a trait level, or should this be impacting them on the state level? And you can have this sort of like cumulative effect, where if you affect them at time 1, there's some like carryover to time 2 that doesn't have to be all trait. But all to say, like, I think there's a case where if you have a pretty firm theory that there should be some development going on, that's one thing, and what I'm talking about is really appropriate. But if you're in these class of things where like they might just be bouncing around, there might be no developmental trends over time, then I would probably model them quite a bit differently, but I would still account for some of these scoring issues that we're talking about. Go ahead, Walter.
I'm gonna hold off until the end because I want to see the final results here. But yeah, I'll come back.
Okay, sure. Yeah, happy to talk more about any issues people have at the end. Let me just double check. Okay, let me show my screen again. All right, so now we get to the part that people care about, which is how badly can this muck up my study results. And so just so people know, this kind of draws on a lot of different research. I'm now both relying on what's in this paper expressly, but also a couple of findings that occur outside of it from other research of ours. And so just so people are aware, these results are going to mix and match empirical examples from the core districts using growth mindset survey item results. And so there'll be a little E there for it being empirical. You'll see that in like the bottom corner of the slide, in case you're wondering, you kind of lose track of is this made up data or is it real? And then also have these results from Monte Carlo simulation studies where we replicate it over and over and over again and see what the results are. And so those have the little S there. And so one thing to note is that pretty much any way you look at these scores, they are almost always correlated 0.92 or above. And so this is, I feel like, is just an important caveat that I often make, is that you can have very, very highly correlated scores and still run into these issues. So, you know, don't think that if you are comparing two scores and they're really highly correlated, you can just say, oh, well, they're basically the same and call it a day, because it often masks important effects. So I'm going to start with a simulation in this single group, single time point scenario. And I'm going to do that just because I think it's kind of instructive and will help make sense of the actual kind of more interesting scenarios going forward when we know the reality of the situation. So here the data were generated with a true mean of 0 and a true standard deviation of 1. And we're trying to see how well we can recover those values. And so here we have the number of people in the study ranging from 100 to 500, 4 survey items up to 12. We have their EAP scores, MLE max, which is where just the software's default is dumping in scores for people where they used only the top or bottom response category. MLE missing, where we just treat those undefined scores as missing, and then the true scores. And again, the true scores are basically like when you do these simulations in IRT land, it'll actually produce the student's true value, these simulated students' true value on this latent continuum that you care about. So we can actually compare all of this to what would happen if you had some of the true scores, but there's still some sampling error thrown in. And there are a few things to note that probably jump off the screen to all of you too. But the first is that if you have this MLE max scenario, you're getting quite biased estimates of your means. So here, when you have really short survey scales in particular, which means you're more likely to have kids who just select the bottom or the top response category, in some cases, you're getting an upward bias of 1/10 of a standard deviation. Whereas it breaks in the opposite direction for missing, MLE missing, and tends to be a little bit smaller. But all of this will be dependent on, just what type of survey measure you're using, how likely people are to bunch at one end or the other. And you can see that this goes down as the survey lengthens. The other thing you can see is that for the true scores, you actually get values that aren't exactly 0. And that's due just to sampling variability. But what's intriguing is for EAP, it's nothing but zeros. It is out to 3 decimal places exactly what it should be in the data generating. So we were, puzzling over this, like, why would EAP scoring, this Bayesian scoring approach, do better than if you knew the kid's actual true score? And the reason is because of the shrinkage that is happening. So here we have a plot of the MLE scores and the variances of these scores. So these are standard deviations, where again, the true standard deviation is 1. And these are the EAP standard deviations. And so what we see is, like, down in this corner here, if you have items, a survey with only 4 items, and this low slopes piece means that those items are a little less reliable compared to some other items, you're going to have a maximum likelihood estimate of the standard deviation that's 1.4 compared to a true of 1. Whereas you're getting EAP scores that are about 0.9, 0.8, 0.9 compared to a true of 1. And so what that's doing is you're getting these, perfect EAP scores, because in the presence of like very short, less reliable survey scales, it is just shrinking those things down such that it's really close to the mean, and you get less bias. And so that might seem intuitively appealing, but one of the things I'll show is that that can actually really affect type 1 errors. So now we move into the case of, that's by way of backdrop. You can get biased means, biased variances, depending on how you produce your scores. And you tend to get inflated standard deviations with maximum likelihood and really reduced, shrunken down standard deviations with EAP, especially when you have these very short survey scales. And so now we'll move to the example of, well, let's say you have two groups and you want to understand, say, male-female differences in growth mindset, which is something that people have debated in the literature. So I produce scores in 4 different ways. There's the total score, there's EAP, so you're shrinking things, but you're assuming there is a single group. So even though you have males and females, we say, well, yeah, but there's just one overall mean and variance. Then this MLE maximum, where we replace missing values with the maximum, some arbitrary value. And again, you assume there's a single group. And then finally, using EAP scoring with multi-group, where it's male and female are the 2 groups. And then looked at mean differences in growth mindset. And so what you end up seeing is, so my animation works, is that what we have up here is your total score, single group EAP, single group MLE, multi-group EAP. And so, a few things to point out is if you look at the total scores, the difference between the two, the means, and so these are medians here in these box plots, but we're talking means here. But the mean is about 0.08 with a standard deviation of 1 for the 2 groups. Pretty similar difference for the single group EAP, slightly smaller standard deviation. And again, that's because these scores are getting shrunken down. So these are behaving exactly the way you'd expect. We're just going to shrink to a single overall mean, which reduces the variances. When we have single group MLE, all of a sudden our differences is jumping to about 0.16. And what you'll notice is there are these really extreme values. And there are a whole bunch of them here, just there, you can't distinguish them because they're all hitting the same plot. But basically, the software we use just said, well, your score is undefined, so we'll give you a value of 4 standard deviations above the mean or -4. And so that also really affects the variability. And then finally, if we have the multi-group EAP, we get our biggest difference of this estimate and a standard deviation of around 1. And so, to cut to the chase, if what you really care about are these group differences, this estimate is more than double the estimate you're getting down here, and your variances will be quite different. These are just sort of variances overall, but they would also mean that your variances are different by group. So if you're doing like a 2-sample t-test, which relies on those group-specific variances, you will get very different results in terms of which are found to be significant or not. And the one other thing to note here is that, again, if you have a total score, that essentially just says, well, whether I said strongly agree to item 1 and strongly disagree to item 2, or vice versa, I'm going to get the same total score. And so with this total score here on the horizontal versus multi-group here, you can just see that for every total score, there's a lot of variability in your actual IRT-based scores. And that's both because we allow the items to have different weights, such that the specific responses corresponding to specific items matters, and because you might get shrunk into a specific group, which might also mean that you could have the same scores but be in different groups and have your scores shrunken differentially. So this is part of what's happening when you use a total score versus not. And just as one more, so this is from simulated data. So let's say we know the truth of the matter, it's a treatment effect that's actually 0.25 standard deviations. What we can see is using some approaches, including the multi-group, on average, so these are like the density plots across 100 replications of this study. Like the density plots tend to sort of hit at the true treatment effect for some of these scoring approaches, whereas for things like total scores or these group models, IRT models that say, we only have 1 group, not 2, we tend to be producing estimates that are in some cases like half of the actual treatment effect. And so one more on this point of type 1 and type 2 errors is that So let's say here we have a case, and these are from the simulations again, 4 items with a sample size of 100, 12 items, sample size of 100, 4 items, 12, but a sample size of 500. And so what we can see is that there are huge differences across scoring approach. So this is, and these are labeled a little bit differently, but this is your total score. These are your single group models. This is your multi-group model. And then this is the true score. And so one of the things you'll see is that there are big differences across scoring approaches. So this is the proportion of significant treatment effect estimates. So we replicated these 100 times. So what this means is that, I don't know, about 25% of the time you get a significant treatment effect estimate from this multi-group model. So you're doing really well here compared to the others. You are also in a scenario, because this is such a short survey, that you're actually outperforming true scores. So you are both more likely to identify a true treatment effect and also more likely to identify something that is not significant as being significant. So you really kind of are in dangerous territory if you have only 4 items and not many people, because the shrinkage is going to be so severe that you're going to detect true effects better, but you're also going to get type 1 errors a whole lot more. Whereas if you have a longer survey, and especially with more people, you're in better stead. You're getting less shrinkage, there's less uncertainty. And so here, your true scores, as they should be, are producing the most significant results. But this multi-group model is only off by a little bit, whereas these sum scores, these total scores are doing poorly relatively. And these models, these IRT models that assume you have one group, are doing terribly. So if you decide to do the principled thing, and then use IRT, but you use an IRT model that isn't acknowledging sort of the data generating process, then in a lot of ways you're shooting yourself in the foot. So now we can look at something like understanding SEL growth, social emotional growth, look at these growth mindset trends again. And again, scored them in a bunch of ways, including, instead of multi-group now, we have multi-time point IRT models that say, wait a second, we should have a different mean and variance at every time point. And so what we see is we basically produce these plots where we randomly selected people from our data, like 30 or so people, and plotted their model-based trajectories. So like this is, we produce scores, we put them into a growth model. We said, what does that growth model say an individual kid's growth trajectory looks like? And so what you can see is that if you use a sum score, you get a pretty good sense of the slope. So the mean slope is about 0.126 standard deviations, but the variability in that slope is only about 0.02. And if you use a unidimensional model, which means a single time point model with shrinkage, you are hugely tamping down any variability in these slopes, and you're really biasing your estimate of the slope. It's only about half of what it is for some of these other approaches. Whereas if you use MLE and assume a single group, or use the multi-group model, multi-time point model here, you can see that you are getting not only a big slope, but huge variability around it. So if you were to use a sum score, you might conclude that there's growth happening, but there's not a lot of variability. People are pretty consistent. Whereas this model tells you, well, hang on a second, there's actually huge variability in how much kids are growing in these constructs over time. And then just to kind of show, this is actually from simulation. So that was empirical, this is simulation. If you use the true scores, this is what the variability looks like. Sum scores, single groups, and then multi-group, multi-time point. And so here we see, like, if you actually account for the fact that you have multiple time points in your IRT model, the variability and the slopes you're getting is just much better matched to what's actually happening in reality. So the final thing, and we're short on time, I want to make sure that we have time for questions, but you might be interested in 2 groups and 2 time points. And so this is your classic control treatment pre-post. I did not have those data exactly, so I looked at male-female gaps in growth mindset. And in simulation studies, you see all kinds of issues like doing a poor job recovering treatment effects. But in this empirical example, looked at male-female gaps in growth mindset and how they developed. And And given we're short on time, I won't kind of go through these because really the story is the same. Like single group, we kind of shrink them all down to a single mean. The variances are really understated. Here we get all these kind of wacky extreme examples because of undefined scores. The multi-group EAP is really the one that seems to be capturing this sort of meaningful variability. And so then if you were to actually produce estimates by time point, so these are grades 5th, 6th, 7th, this is the male female difference in growth mindset. If you use a total score, you see, yeah, the trends are pretty similar. That there's initially a gap favoring females, but by the end it's favoring males, but none of it's significant. Whereas if you use a single group EAP, you see similar trends with a couple significant results. If you use the multi-group EAP, huge different in this initial gap estimate, and you're getting significant results in 5th and 7th grade. So I'll just a couple quick concluding thoughts and then open up to questions. I mentioned these possible motivators, including longstanding debates in education, replication, like all of these factors could be, these scoring choices that I've been enumerating could be affecting all of these things. And so, I don't really think and want to overstate the case here. I don't think measurement and how you're scoring is driving these issues necessarily, but it's also hard for me to believe it's not contributing in some meaningful way to some of these disagreements we get in the literature. And this is a giant table, but all to say, like, I walk through sort of the trade-offs, we walk through the trade-offs and like all of the different choices by study design and stage in the paper. And then the last thing I'll say is that like all these problems I'm describing, I think are actually compounded in a lot of ways when you have multiple raters. Because, so you have a case of like teacher observational protocol, and you may have one or more people observing a teacher because, as others have pointed out, I think this is one of Andrew Ho's studies, he basically shows that there are all these sources of variance. There's the teacher, there's the item, there's the rater, all these sources of potential error in your estimates. And you could fit an IRT model that accounts for these differences, but most of the time we don't. And so you're baking in these different sources of variance that are pretty irrelevant to what you care about. So hopefully the presentation gets shared. I've got some citations to some of my work and my joint work that might be helpful to people as you think through all of this. That's it. That's what I got for you. So thank you very much for the attention, and I'd love to chat with people if there are further questions.
Thanks so much. Let's toss it to Walter first, though, because I know you held off mid-presentation, and then from there we'll open up after Walter.
Yeah, and I'm not sure how I'm thinking of this from like in I guess like quote unquote achievement assessment perspective, and like using administrative data, which is of course what I and I think many like policy researchers tend to use. And I was just struck that for all of this, you can correct me if I'm wrong, but it requires item level data, which generally I like don't have access to, for example. And so as I was thinking about this, I guess two things come to mind. One is a kind of naive question, which is like, when I use scale scored results from state standardized assessments, SBAC, PARC, those sorts of things, are these sorts of measurement models baked in to those scale score results such that that's like less of a concern? So hopefully that's a quick one to answer. And then the second question I'm thinking about is for when that's not the case, I'm just like in a systematic way, sort of, on whom does the onus fall to, account for these things? Is it researchers after the fact? Is it, whoever is administering the assessment, those sorts of things? So thinking about that too.
Yeah. Thanks for both questions. Let me know if I don't answer them in their entirety, but I think it's really tricky when you don't have item level data. Like oftentimes we inherit data from other people. And that's one reason that this can also be more relevant to survey data, is that I think it can oftentimes be a little easier to have the item level survey data, because it oftentimes tends to be a study that or survey that you've produced a little more frequently. But with something like achievement tests, first off, you will run into some of these issues, but not nearly as many, because, for example, like I mentioned, unless you have an extremely hard or difficult test, you're not very frequently going to be getting kids who are getting all of them right or all of them wrong. If there are, that's a reason for concern, even just leaving aside the IRT piece of it and why computer adaptive testing is so important. But it is important to know that those achievement tests are almost always going to get scored with maximum likelihood, because they're for individual uses. Like, you want to give a kid their score and know that it means something. So we're not going to shrink them and introduce bias in that way. And it's important to know that oftentimes those will lead to overstated variances and reduce the likelihood that you detect some true effect size, some true effect if there is one. And so even if you can't access the item level data, this goes back to Vivian's question. I think ideally for any study, you would at least report, what IRT model was used and how it was scored. So we can at least say, well, it's like, Walter used, map growth, which was scored using maximum likelihood and was computer adaptive and all this stuff, so that we can say, well, there's some pluses here. You're not really, because it's computer adaptive, not really going to know or run into a situation where someone has an undefined score. But because it was maximum likelihood, like, if you have a treatment effect that's on the cusp of being significant but not quite there, then that might just be because you weren't able to rescore the item such that it matched your study design. So all to say, like, you might not be able to address this in good conscience in your study at an item level data from that perspective, but we could at least know which way the bias is likely to break if we know something about how the scores are produced. Did I get both of them? Kind of, sort of.
Yeah, no, I think that's really helpful. Yeah, and I'm also recognizing maybe there was a lot of overlap with that question and Vivian's too. But thanks, Jim.
Yeah, absolutely. Any other questions from folks?
Jim, are you able to copy and paste the link to the paper in the chat? Because I seem to remember you said there was some guidance on implementing this stuff in there.
There is. Yeah, let me see if I can.
I can do it for you. I have it on the website. Feel free to answer other questions. Yeah.
Thanks,
Okay.
Jim.
Appreciate it. Yeah, and I don't know what the protocol is around sharing slides, but I'm happy to send them your way or have them sent to everybody. One thing to note on that link that Shannon has is that we have since, one of Kelly's contributions is, since that was posted, we've produced our code to produce some of these models. So before, it was originally just FlexMert, which is proprietary, and so now there's at least some open source software. And as a quick aside, I'd be totally happy, like, if people are interested in this and fretting about it at all. I haven't looked at what options Stata provides in its IRT package, but I would bet we could replicate it pretty quickly there too. Go ahead, Vivian.
Thanks, Jim. I always enjoy watching you present. I had a question about model selection and how you decide what the most appropriate model is. So it seems clear to me that when, for your study design, that I guess you would select a model that sort of resembles basically your study design. But with the multi-groups, if you're potentially interested in males and females or students with disabilities and not with disability, like, you could have lots of groups, and it could, you could allow for increased flexibility in your model, but it seems like that could be pretty noisy. So I guess, do you have guidance around how people should be selecting sort of their models for scoring?
Yeah, definitely. I think there's a technical piece to that and a theory-based piece to it. The technical piece is IRT doesn't tend to give good fit statistics, but something like structural equation modeling provides a lot more options in that front. So if you're really concerned about selecting the appropriate model, you could, fit a couple of the different types of models that I suggested and just see which one fits better. And that's one of the things that's interesting about like Dan McNeish's article, is that if you actually treat total scores as a measurement model that's just extremely constrained, like you can fit that, and most of the time it just fits terribly. There's, you can tell right out of the gate that that is not really justifiable given what you have in your data. But there are also going to be times when the fit statistics are inconclusive, you're just not sure what to do. And there, I mean, I would imagine it's a lot like when you're just doing regression or something along those lines, you'd probably want to rely on theory as much as you can. And so, like, if I'm doing a randomized control trial, do I know for sure that we have multiple groups where they'd have separate means and variances? Like, no, but we've come as close as we can to actually generating the data that way. And so as far as theory goes, I think you're on firmer ground to select sort of a multi-group IRT model, because theory-wise, you should be seeing different means and variances between the two groups. Does that help?
Does help. Thanks.
Sure. So, I think we got a minute left. Any other questions or? All right. Well, I really appreciate everybody's attention. I'm as ever happy to talk about these issues if they crop up in your work. One of the things I like about measurement is it cuts across pretty much everything. So if this raises questions for you and you want to have continuing conversations, I'm always happy to do that.
Thanks, Jim. Thanks, everybody.
Thank you so much. We appreciate it.
Thanks, guys.